We have seen in the propagation that we use the gradients of the coast function with respect to the weights to update the weights. But there are a few problems related to these gradients, and they are manifested in this kind of behavior, like the one we have in this figure. So as the number of iterations go, here are in 10,000, so 10,000, 20,000, 30,000. So at the beginning it is learning quite a lot. So this, for instance, let's say that we have a feed-forward network, just a standard dense network. So at the beginning it learns, but then at some point there is a big jump in learning for the training, but we see that it saturates for the test, and the same happens no matter what is the depth. So 56 or 20 layers, they also saturate, so they don't learn anymore. So when they don't learn anymore, it means that the weights are no longer changed in a meaningful way, so that the test error and the training error have converged to a region where the gradient is zero. Okay, so, but this problem of having zero gradients very often happens in even if the network has not converged to a good solution. And the problem is related to the derivatives of the activation functions. So at some point we have the derivative of the cost function or the activation function with respect to the argument. So we are talking about these terms here. So A with respect to Z, and no matter which layer we are. So let's say that this is our activation function. So the activation function is a sigmoid. At some point it saturates between 0 and 1, so beyond -4 it is almost 0, beyond 4 it is almost 1. So if our set is such that it falls in this region where we have so Z is close to 0. So if Z is close to 0, then here we have a lot of slope in the sigmoid function. So that means that if we are making errors that are positive, then we want to decrease the weights so that next time the set will be smaller, so that we have smaller errors at the end. And the same if our error is very negative, not very negative, but slightly negative, then we want to increase the weights so that the set is larger, and then we move forward, we move in this direction, so to higher values, so that the error is smaller. But the problem is if our function, our set is here. So if our set is here, that means that no matter how we move the weights, there is very little change in the output. So this A with respect to Z is very small. So we don't know where to move, so that so how to change the weights so that the error is smaller. And this is a problem of saturating functions. So the hyperbolic tangent and the sigmoid activation functions have this problem. So we don't like to be in the region where it is saturated, but in the region where there is a good slope. ReLUs don't have this problem, and that is one of the reasons why they are so popular. But they have another problem, that is the exploding gradients that we will also see. And here you have a web page where they discuss all these issues in quite detail. So the vanishing gradients is a problem in which you see large changes in the parameters of the later layers, so the layers that are closer to the coast, whereas parameters in the earlier layers, they change slightly or they stay unchanged. So as you are propagating back the gradient from the coast to from the last layer to the first layer, it is getting less and less and less prominent. So in some cases, the weights of the earlier layers can become zero as the training goes. So at the beginning, even the weights go to zero, so that there is nothing that propagates through the network. And the model learns slowly, and very often the training stops after a few iterations because the goal function is not changing anymore, and the model performance is generally poor. So the solution, there are several solutions. So one of them is to decrease the number of hidden layers. The other one is to use non-saturating activation functions. The other one is to initialize the weights in such a way that the first sets that are calculated a little bit at random, they are here, so that we are in a region where there is a maximum slope. And increase the learning rate in the first layers. So in the first layers where the gradients are smaller, you increase the learning rate, and that is what Adam Optimizer is doing. And another solution is to use this batch normalization. We will see more solutions later. For instance, this skip connections is also one of the solutions. So batch normalization has been found to help this problem of vanishing gradients. So the initialization, we saw it in the example that we had a few lectures ago when we implemented the perceptron, not the perceptron, the multi-layer feed-forward dense fully connected network with from scratch. So we had to initialize the weights. So we initialized the weights and the speeds and everything in this. So the speeds to zero, but the weights are initialized in this way, in which we have a Gaussianly distributed random number that depends on the number of inputs and the number of outputs, and then it has some power. And there have been a few suggestions for these powers. So for instance, this one is 2 divided by the number of inputs, and here 1 divided by the number of inputs. Here it is an average between number of inputs, number of outputs. And yeah, so in general it is a random initialization, but relatively close to zero and with positive and negative values, so that the first sets are more or less in this region. And it also depends on what is the normalization of the input values. So the input images or the input signals to the neural networks, they normally are supposed to be zero mean because of this, because you want to be in a region where you have maximum slope. If your inputs are in the range of 1 million, then and all the weights were positive, you would be very far off in this saturated region. Okay, so initialization is one of the solutions. Then we have the opposite problem, that is exploding gradients. So the ReLU, for instance, doesn't saturate. So the problem is that the gradients become very, very large, and they start to get larger and larger as the iterations go, and then the weights can become not a number very quickly, so you go away from the set of numbers that can be represented with floating points, and it is a divergent behavior. And also the model loss goes to not a number, and so on. So one solution is to clip the gradient. So if the gradient has a module that is a very big, you clip it and you give a maximum value, and this value can be one, can be something that makes sense in your context. And the other one is to regularize the weights. So you have a loss function, but then you also have, then you add to it the norm of the weights. And if you use the L2 norm, normally the weights tend to go to relatively small numbers. And if you use the L1 norm, even you can have sparse networks in which many of the coefficients are zero and only a few survive and give the output. We have mentioned this batch normalization. So here we have the standard network, we have the linear part and the activation function. So this is the nonlinearity. And then what you put in between these two is a batch normalization. So this batch normalization behaves like this. So it has a set of inputs. So let's call these inputs yj. And then for the batch, so you can think of this, that you have a vector for every, so you have an input, this input propagates, and then at this point you have a vector y, and you look at the jth component. But you normally work in batches. So here you don't have only one vector, but you have, let's say, 64 vectors. So these 64 vectors, you look at the component j, and then what you are doing here is a standardization. So you subtract the mean of that component along the whole batch, and you divide by the standard deviation. So this one tends to have something that is centered around the mean and has a standard deviation 1. And then there are a couple of learnable parameters, this gamma and beta. There would be two parameters that the network has to learn. So beside the weights, we have now to compute the derivatives with respect to gamma and beta and update them. And here you have how the accuracy, for instance, changes. So in the standard learning, the training the training accuracy improves, but the test accuracy does not improve, and that is a clear reason, a clear indication of overfitting. And here we have used this learning rate, here with a different learning rate, and batch normalization. So it is independent of the learning rate. So you see, with batch normalization, with this learning rate, it is learning better, but also here it is with batch normalization you are getting better. Sorry, this is training, so this is not test. Okay. So in the standard, it doesn't learn because it has this vanishing gradient, but with the batch normalization, you learn, and you even increase the set of coefficients for which you can learning rates for which you can converge. So there are some other regularization techniques that are very useful for this: dropouts, adding noise to the internal variables. So here the y, for instance, you can add some little noise so that it has to learn despite this noise, it has to learn, and pretty often it is something useful. Stochastic activation functions. So the activation function is not a fixed deterministic one, but it has some randomness in it. So all these things normally they help with the problem of the gradients. There is another problem, that is this sharded gradients. So in the vanishing gradients, the gradients shrink to 0, so you have no gradients. In the exploding gradients, the gradients grow exponentially, so you diverge. And the shattered gradients is a problem in which the gradients retain the magnitude, so they don't go to zero, but they lose directional coherence, so they become more and more like random noise. And for instance, in this paper, they have shown that these ResNets, that are networks in which there is a skip connection, we will see it now, they help to solve these shattered gradients problems. And then here they show one layer feed forward, and the and they show that the gradients are not so when you have only one layer, there are no problems with the gradients. When you have 24 layers, the gradients become very noisy. And even here, these 50 layers, so many more than 24, but now you have skip connections, and the gradients still make some meaning. And these covariance matrices somehow indicate that there are neurons that are correlated to each other, which makes sense because the information is not, for instance, in images, they are not completely spatially uncorrelated. On the contrary, they are very much correlated, and the correlation somehow has to propagate through the network. So these layers Y or Z, they also need to have some correlation, and this correlation is preserved even in the in very deep networks. Okay, so what are these skip connections? So typically neural networks learn y as a function of x, and here theta are the weights. So why not learning y as a function of x plus some function? So that means that we are saying y should be similar to x plus some modification. We have to learn this modification, or this residual. This is also called a residual. So our blocks now will look like this. So we have x, and then here we have x plus f of x, and f of x is this thing. So we have a weight, then ReLU, and then some weights, and then we go into the addition with x. So the residual now is learned by these weights, by these learning residuals, and then you can be very creative in how you make the skip connections. These are called skip connections. So how do you make your skip connections? So you can do it like in a unit function fashion, or you can do it in this way, in which there are skip connections from this block to this block, but also from this block to all these other blocks, and then you can be really creative here. And with these skip connections, you can train very deep networks, because the information somehow, the gradients, they do not vanish if you don't have the skip connections and you have a very deep network. Here you know how to change the weights in this layer to change your loss function, but as you go deeper and deeper in the network, these gradients, you don't know how to what is the effect of changing a weight here in this first layer to the very last layer, and the calculation of the cost function. And here so it is another way to look at it. So how you establish the skip connections, it is up to you. And here, for instance, they have studied what is the goal function, the goal function landscape, as you add skip connections. And then so here in the axis you have the weights, and then what you see is that the landscape, so how the cost changes as a function of the weights, is much smoother if you have skip connections compared to if you don't have skip connections. Still you have local minima. So this is a local minimum, this is a local minimum, and this is a global minimum. But so you still have global minimum and local minima, but you have many fewer local minima, and the landscape of the coarse function becomes smoother. And adding is not, so the addition that we use here is not the only way to use to use the skip connections. You can also concatenate, for instance. So let's say that you have some information, then some residual information, and then you can concatenate the two so that the next layers, they have access to the two pieces of information decoupled, because with the addition we are coupling them, and we are constructing a vector in which the two pieces of information are not separable. But now in the concatenated output, they are decoupled. So the next layers can pay attention to some parts of the input or some parts of the residuals or whatever they decide. So with this we finish this part of gradients, and then we move to the next topic.